Hello and welcome to section 7.1. In this video we'll be going over example 1 and we'll also be introducing internal forces. So we've already seen one type of internal force in chapter 6, and that was the tension and compression forces, which we will be calling the normal or axial forces. They act along the axis. So these would be, in this case NB in this diagram, that would be our tension and compression forces when we cut through the members. So if you remember in the last section, I think 6.6, we said we couldn't cut through multi-force members because we would create additional internal forces. Well, this is what's happening here. This is a multi-force member. We have some loading here at the end, but we now have these loads P1 and P2 that may not be acting at the ends. They may act somewhere in the middle. And so if I cut this beam, I still get tension compression, NB here, but I also get a moment and a shear force. So shear force is with this V term here. And just like everything else we've been doing, whenever you cut something in half, when you put it back together, your internal forces should cancel out so that you get a rigid body. So that means forces should be equal in magnitude, opposite in direction. So for instance, the moment here goes this way, but the moment on this side of the cut goes this way. Now there are directions for these as far as what is assumed to be positive. So like in an X direction, we assume right is positive. For Y direction, we assume up is positive. So in 3 dimensions, we get the same thing. We get a normal force, which is actually an axial force, which would be tension or compression. We get shear in the X, shear in the Y, and then we get bending moments about the X, Y, and Z axes. So we still get 6 forces internally. One of them is along the axis, and the other 2 are shear, and then 3 moments. So sign convention. So sign convention is arbitrary, but this is what is commonly accepted. So when you cut something in half, tension force will be considered to be positive. When I label shear, so if you imagine that the beam is pinned, so if I'm working on the left-hand side of the cut, then it will cause it to rotate clockwise. If I'm working on the right-hand side of the cut, I imagine that it's pinned, it'll make it rotate clockwise. So if the shear force would cause clockwise rotation on the half, and so I'm saying left and right, but it could be a top or a bottom cut as well. We do work on things that are vertical occasionally. And then the last one is our moments. So a positive bending moment, so if you imagine that this is, say, fixed to the wall over here, and I tried to apply a force, I'd be pushing down here. Well, then this beam, I'm going to exaggerate it, would bend like this, where it's still pinned to the wall over here, and I now have that external force pushing down on it. So it'll create a happy face. So a happy face is positive, a frowny face is negative. So it says up here, upward bending, basically it's going to create what looks like a happy face, and then we consider that a positive moment. Alright, so again, those are arbitrary. They'll matter more when we get to the next section when we actually do shear moment diagrams. So let's look at example 1. Example 1 and group problem 1 ask us to work on drawing these free body diagrams on these multi-force members. So we can see that we have forces at the ends here. We have a roller, and we have a roller down here. We have a pin joint down here, and then we have some forces acting in the middle. So this is not a 2-force member, it's a multi-force member. I have 10 pounds, and then I have this distributed load of 2 pounds per foot. I'm going to cut this at 2 foot, so I'm going to cut it halfway here. So I'm going to make a cut right there, and I'm going to draw the left side of the beam and the right side of the beam. So let's do that over here on the visualizer. So again, we're going to cut this beam at 2 foot. So roughly here. And then I'm going to draw both sides of the cut. Normally you'd only draw the sides you'd want to work on, but you may not know what that is yet, so it's okay to draw both sides until you get used to things. So I will just redraw the beam over here. So I've cut this beam, so I'm going to kind of exaggerate that it's been cut. And I have these external forces up here. So this is still 2 pounds per foot. I'm going to go ahead and draw my reaction forces here at, well, we can call it A if you want, so I'll go ahead and label it A here. I don't know if it's A on the diagram. I'll have an A and a B. If they don't exist, you can always make up points if it helps you kind of talk about things. So I have A, so I'm going to make an AY, and I'm going to make an AX. Okay, so I'll have an AX and AY, so that's reactions because of this, so those still exist, and then I will have all of these forces. And then, if this was a two-force member, we would get our tension force, so we're just going to get a tension. And so we might call this point here that I cut at, I'll call this point C, C for cut. So we can call this tension C. And so that's pretty easy. That's pretty easy to see. Now we got to put the last two pieces in. So our shear force, so that is, you could imagine a, so I have these magnets here so I can kind of show that. So I have these magnets. So our shear force would be as pushing down in a sliding. It's kind of a sliding motion. So they shear. It's how scissors work, kind of. So we established that a shear force that causes a clockwise rotation, so we're going to be pinned here at A, we're going to imagine, because our cut's here, so we're going to always work on the opposite side of the cut. So we're going to say if I rotate around this way, that would be clockwise. So a downward shear force, and shear is not an S, it's a V. So V of C. And then the last piece here would be the moment. And again, we want to make a happy face. So in order to do that, we'd want to push down in the middle. So we'd want to have our moment come up and kind of. So again, imagine this side over here is fixed, and we're going to grab it with our hand, and we're going to like torque it. I'm sorry that the visualizer froze there. Maybe it'll come back. There we go. So we'll get a moment at C. So that's the left-hand side. So let's draw the right-hand side. So I'm going to leave some space, and I would advise you to do the same thing, because it can get kind of condensed in here. So this is still point C here. This is both sides of point C. This is point B over here. Point B is a roller, so we're going to have an external force By. I'm going to have this 10 pounds acting here. So this 10 pounds carries over. And I'm going to have the other half of this set of forces here. So my dimensions are a bit off on this, but it's okay. Still 2 pounds per foot. And now when I come over here to this side of the cut, once you get one side set up, you don't even really have to think too much over here. You just make it opposite direction, equal magnitude. So this would be tension C. This one went down, so this one has to go up. So this would be shear C, and this one went counterclockwise, so this one has to go clockwise. Moment C. Again, when I put this cut back together, all of these internal ones, tension C, shear C, and moment C, should cancel out. And then the last thing I need to do here is add in dimensions, so I know how large everything is. So this is 2 feet. This is 2 feet. And then from here is another 2 feet. Again, like I said, the dimensions are a little bit off. I'm sorry about that. And then from here to B, it looks to be 4 feet, because this was originally 6 feet over to 10 feet. So that would be your free body diagram. Next thing you'd probably be asked to do is find these internal forces. So what you would do then is you would count up unknowns, and we'll do that in the next one. But just real quick, on this problem, on the left-hand side we have 1, 2, 3, 4, 5 unknowns. On the right-hand side, we have 1, 2, 3, 4 unknowns. So which side would you work on? Hopefully you said the right side. So I'd work on this side. So these are rigid bodies. So you get to use forces y, forces x in moments about points. So you'll have 3 equations there, and which means you'll need one more equation. So what you would most likely do in this case is you would go up here, do moments about A to find by, bring that by down here, and then solve just this diagram once you had by. And then before I jump off, let's just talk about your group problem here. So in this case, if you were drawing this, so now you're going to cut here at 6 feet. So let me grab a pen. There we go. So let's just imagine we are looking at our beam here. So I'm going to ignore the internal forces. You should hopefully know how to do those. They'll be the same thing as we just did. So the difference is going to be this 10-pound force. So what you don't want to do is you don't want to put 10 pounds on the left side of the cut and 10 pounds on the right side of the cut. What will happen then is when I put the beam back together, I will have 10 plus 10, which is 20 pounds. This is only 10 pounds. So you could put 5 and 5 on each side. Most of them what they're going to do is tell you that to assume that you cut just to the left or just to the right of the force. So in this case, they are telling you assume that the 10 pounds is just to the right of the cut. So we would keep it over here, and we would erase this side. So we wouldn't have it over here. So those are the 2 most common ways to handle it, is you just put it on one side or the other, or if you really wanted to, you could split it in half, and so you could have 5 and 5. Alright, if you have any questions, feel free to contact me.